So we talked about all those different path searching algorithms, depth first search, breadth first search, Dijkstra's algorithm, and A*. And so I've kind of finished my coverage of those for now, so I'm not going to go back to those at the moment. But I want to teach you about another thing called spanning trees and an algorithm related to finding them. It's called Kruskal's algorithm. And just like A*, I also did not invent this algorithm either, just to be really clear. OK, so let's talk about a new term here. A spanning tree is when you look at a graph and you make sure that the graph has the following properties. It has only a set of edges necessary to connect all of the vertexes but have no cycles in it. That's a spanning tree of the graph. So if you look at this graph right here, I wouldn't call that a spanning tree because basically I can find a cycle in the graph. I can loop back around from U to U. And that violates the definition of what a spanning tree should be, right? Also, if any of the vertexes were not connected to any of the others, that would also violate the definition. So how do I turn this graph into a spanning tree? Well, I just remove edges until it satisfies, right? Like, what edges could I remove to make it a spanning tree? I guess individual edges won't help, but maybe a collection of edges. Like, did somebody want to tell me what edges I could chop out of here? I should make you vote with Socratic, right? I've named them A through, let's see, I guess that's not enough. You need more than, you need more than that many letters. What edges can I remove? Yes?
I think D, E, and G.
Dig. If I delete those three edges, am I OK? I think so, yeah. Now I have a wraparound from Y through to U, and then up to V, and then around to Z. Yeah, that looks pretty good. Sure, thanks. So there's another one. I mean, there's not just one for that graph. You could do it different ways, and those would both be fine. Okay, so those are spanning trees. So, I mean, there are different applications of why you might want a spanning tree, right? Like, can you imagine a real-world scenario where you might want this or care about this? Like, what would be an example of a graph where you wanted it to have this shape, or maybe that would be a useful thing to have? Yeah, you have an idea?
Yeah, you want to take advantage. Actually, no, I'm not right. Never mind.
OK, he hit undo on his answer. That's OK. It is kind of hard to think of one. This might seem like kind of an abstract thing to talk about. Well, maybe we'll give you an example. Like maybe if we're connecting power to different components in a home or something like that. Maybe all I care about is that they're all connected, that everything receives power. And I don't need something to receive 3 lines of power. It just needs to be connected to the circuit, and then it'll receive energy. So maybe I want to come up with a way to do the wiring where I don't have to waste any wires or something like that. I don't know. There's lots of examples of things like that, flow models that might be similar. Do you have another comment?
No, I just in section 3 we learned that we were taught that undirected graphs are by nature always cyclical.
Are all what?
Are always cyclical because you can always trivially engage in a cycle.
Oh, OK. So you're talking about, is it a cyclic? Like if I have an undirected graph like this, can I always make a cycle by just traveling the same edge both ways? Well, by definition, I don't know if that's true. But I think what your section leader might mean by that is that in our library, if you want to make a graph that has no directionality to it, it doesn't directly support that. The graph library in our Stanford package is a directed graph library. So if you want to simulate an undirected graph, you basically add 2 directed edges. And whenever you do that, you basically are making it so you could travel one of them to get to one direction and then the other one to get back. And so technically, you're allowed to do that because they're separate edges. But in most definitions of cycles, you're not allowed to travel on the same edge twice. So if it literally were a single undirected edge, if I used it to travel this way, I would not be allowed to use the same edge to travel back. So I think that comment made by your section leader about all undirected graphs having cycles, I think was more of a comment about our implementation of them. And in fact, that would potentially be considered a flaw of our implementation. And I guess I would just say that our implementation was targeted more at directed graphs, I guess. Anyway, that's a spanning tree. So, oh, I guess I've got a Socratic example right now. Let me ask you this Socratic question. So how do I get those marks to go away? If you didn't sign in, I'll put the sign in up again at the end of class. Let's do a multiple choice problem. And how many of these are spanning trees? I'm going to ask my fiance to see what she thinks. She usually knows the answer to these things. Let's see what you guys are voting for. Vote in if you haven't voted yet, please. Give you a few more seconds. Mariana thinks it's B. She hasn't seen the question yet. You guys think it's mostly A and B with a little bit outside of that. So let's look. That means A and B means none of them or one of them. How about the first one? Is that a spanning tree? What's wrong with it? I guess you can go around it in a cycle to get back to the start, right? So you can't have any cycles in a spanning tree. How about this one? No? It's got a cycle too, right? How about this one? It's not connected, right? You can't get from this part to that part. We call that a bipartite graph when all the vertexes are in one of two clumps. But anyway, yeah, I think none of these are spanning trees. So I guess A is the right answer. Okay, so a minimum spanning tree is basically a spanning tree, but it has another additional constraint attached to it. That is, if you looked at all the weight of the edges that form the spanning tree, that has to be the minimum possible combined weight that could be used to produce a spanning tree for that graph. So, do I have an example here? Well, this example is stupid because I don't know what the edge weights are, and the whole point of this is to minimize the edge weights on the graph. So I don't know why my picture has letters on the edges. I should have put numbers on the edges. I guess my point would be, like, if there were two ways that you could do a spanning tree, like if you, I think the one that you guys told me was the one that went like this, right? Wait, no, I cut that edge. You told me to cut DEG, I think. So if I had this spanning tree, and then if I added up the weights of all these edges, then whatever that sum is, it better be true that I can't make a spanning tree that has a smaller combined weight than that. If I can make one with a smaller combined weight, then that other one is the minimum spanning tree, and mine isn't. You understand? You might be able to make more than one minimum spanning tree. Maybe there's equal ones. There's two different ones that have the same combined weight. Fine. Then those are both valid minimum spanning trees for that graph. Okay? So how many minimum spanning trees does this graph have? So wait, let me reset my Socratic and let's vote again. Multiple choice. Okay, take a look at this graph. Boy, that's a lovely picture, isn't it? What was I thinking when I drew this one? So I guess the vertexes are A, B, C, D, E, F. I don't know why there's no circles around them. And then the edge weights are written in on there. So yeah, how many unique ones can you find? A little trickier than the last one. I'll give you a sec, and then I'll show you the votes. What did you say? You said mostly A's and B's with a few C. Okay, so let's, I don't actually have the answer in front of me. So that's probably okay, though. That means we can figure out the answer together, right? So tell me a minimum spanning tree for this graph. I guess you could tell me what edges to delete, somebody. Yes?
Delete C to E and E to D.
Delete from C to E and from E to D. But then how do you get to E? So if I just delete C to E, is that a minimum spanning tree? So I think it's a spanning tree. Do we believe it's a minimum spanning tree? Can you get one cheaper than that? I mean, the total weight of that is going to be, I mean, sometimes I like to draw it in terms of the edges that remain, right? These are the edges that remain. And so what's the total weight of that? 3, 6, 7, 10, 17? Can anybody find a spanning tree cheaper than that? Okay, so that's one. Is there another one? Yes?
The edge from B to C.
From D to C or from E to C? From B to C? Okay, sorry. I can't hear very well back there. So you said keep the C to E edge, but delete this edge? Like that? Yeah, that looks good. And it's the same weight because the weight of the edge we threw out was the same. So that's a second spanning tree. Any other spanning tree? Yeah? Do you have your hand up? Somebody? Oh, in the back. You got your hand up. Yeah, go ahead.
There's D to E.
Delete the edge from D to E, but keep that one. Yeah, delete this one. So I think that's also going to be a spanning tree. Yeah, that looks good. Are there any others? I think that might be it, right? There are 3 of them. So it's B, I think. Anyway, that's the idea. And it wouldn't count. I mean, you might have thought, well, like, wait, what if I kept all these edges, but then I delete this edge? What do you think of that one? So I cut this edge here. Yes?
Not a minimum spanning tree because it has a higher combined edge weight.
Yeah, it's totally a spanning tree in the sense of getting rid of the cycles. That part's good. But the weight is too high because I delete an edge with weight 1. So the net cost here is a little bit higher than those other ones. So it's not minimum. Right, exactly. So, okay. Anyway, that's the idea of what a minimum spanning tree is. So now let's talk about, how do you figure out what a minimum spanning tree is in a graph. Like if I give you a graph that has too many edges, how do you turn it into an MST? There's an algorithm for doing this called Kruskal's algorithm. And it's actually a fairly simple algorithm to understand. It's a little bit harder to code than it is to understand the verbally, but hey, I'm going to make you code it. So that's where you come in. But I think at least the idea of it is sort of straightforward. Here's what you do. If you have the graph in your hands, you temporarily or conceptually remove all the edges from it. And then you place all the edges into a priority queue that's sorted by the edge weight. In other words, the cheapest, least expensive edges are going to pop out of that priority queue first. And the most expensive edges will come out last. Okay? Now you have a loop that says, while the priority queue isn't empty, pull an edge out of it, which will be the minimum weight edge that you have not yet looked at, and look at the 2 vertexes on the endpoints of that edge. And if those 2 endpoints cannot reach each other yet in the graph you currently have in front of you, then add this edge back into the graph. But if they already have a way of reaching each other, do not add this edge back into the graph. And when you're done, you'll have a minimum spanning tree. That's it. That's the idea. So here's an example of a graph. And I want to just walk through it together and figure out what the algorithm would do. And so to keep it a little simple, I mean, there's all kind of different edges here. And what I've done is I've given the edges names that are letters. And I've also given them weights that are basically their number of letter in the alphabet. So it'll be easy to remember which one comes first and which one comes second and stuff like that. Okay? So you put all the edges into a PQ. And I don't think I'm going to write the whole priority queue out. I mean, the priority queue, would equal, you know, A with a 1 under it, and B with a 2 under it, and C with a 3 under it, and all the way up to, I don't know what's the, is it 16? P with a 16 under it? And we would pull them out in that order. That's just because I made the graph that way so the slide would be easier for me to write all of this out for us. So remember what the algorithm does. Look at the edge. If the endpoints of the edge are not connected, put the edge back into the graph. So let's pretend for a second that all the edges are basically gone. The grayed out edges are gone. And I'm going to color red if we put one back in, okay? So the first edge that you look at, I mean, nobody's connected to anybody. They're all just floating loose right now with no edges. So the endpoints of edge A are these two vertexes, and they're not connected, so I will add edge A back into the graph, okay? Now I do B, edge B, which is over here. These two vertexes aren't connected to anything, so I'll add edge B back into the graph. Next I do edge C. Edge C connects these two. And I mean, this guy here on the left edge of edge C is connected to some people, but it's not connected to this other endpoint yet. So I will put edge C back into the graph. Now we do edge D. D connects from this bottom left vertex to the one to the right of it. This guy's not connected to anybody yet, so I'll put him in like that. Okay. Now I do edge E. Here's, I think, the first point where it makes the other decision, right? I look at edge E, and it's like, I can already get from this vertex right here to that vertex right there by going around the side there. So I don't need to add edge E into the graph. So I'll just leave it out. I'll skip it. Okay? And we just keep going. Edge F, this guy's an orphan, so I'll add edge F in. Edge G, I can already get from the one to the other, so I skip G. H, I can't get from here to over there. Do you see I have this little cluster, this little clump of vertexes here who can all reach each other on the left, and I've got a smaller clump of ones on the right? Well, right now those two clumps can't reach each other, but if I'm on H, that's the bottom right one here. If I add H back in, those clumps are now all one clump. That's kind of good. Now edge I gets me up to this new vertex that I couldn't reach before. Edge J I don't need because I can already get there. Edge K gets me over to this guy. Edge L, is there an L? It's right there. I'm getting old, you know. I couldn't find it. It's down here. We don't need that one. What letter comes after L? M? I think I don't need this edge, right? Because I can go all the way around and get there without that edge, right? Just for perspective, keep in mind, like, okay, that's a weight of 13. If I went all the way around, that would cost more than 13, but that isn't the point. It's not to say that I can get there just as cheaply some other way. It's that I can get there somehow. I'm looking for the minimum total overall spanning tree with the fewest necessary edges, right? So I leave out edge M. And then N, I think I don't need N either, right? Because I can go around the corner to get between those two. Edge O, I don't think I need. And edge P, I guess I need that because I haven't got this top guy in here. And then edge Q, I think that might be there's Q I don't need because I can already reach them. And R I don't need because I can already get from there to there around the side. So I think that's it, right? R was the last edge. I thought it was P down here, but I missed a couple. But anyway, that's the way the algorithm runs. And if you just look at which ones are red, if you just kind of look at it for a second, I mean, I hope you could convince yourself that that's a spanning tree. Like, I can't find any ways to cycle around on that. And just by the nature of this algorithm, we will know that this would be a minimum spanning tree. Can you kind of convince yourself why that would be true? What gives you confidence that, other than the fact that I'm teaching you this today, so it probably is legit. Other than that, like, what would make you think that maybe it's likely that this would be a minimum spanning tree? Like, what part of the algorithm gives you confidence in that? What do you think, sir? You're starting
up by adding the smallest weighted edges, and you just increase the weight only when you absolutely need to connect something into the tree.
Yeah, like you said, like I'm increasing by the least amount of weight possible each time. I'm pulling things out of this priority queue in increasing order of weight. So it's kind of like I'm going to find the cheapest possible way to attach each new person to my clumps that I've already been building. And if I have a cheaper way already, I don't use the more expensive way. So the priority queue is important. If I just threw all the edges into a queue or some other data structure that weren't ordered in the right way, I don't know if I would guarantee that it would produce a minimum spanning tree as its outcome. You know? So that's the algorithm. And I mean, that's it. So, like, I guess the part that makes me, that makes this more interesting is when you actually have to implement this. It's a little trickier. I mean, that's the point of pseudocode is you skip all the nitty-gritty details, right? So maybe we could talk about the details in a second. Oh, look, this is cool. Look, if I go from my slide to the next slide, it draws the one that we made. So I guess we just wasted our time. We didn't need to do that at all. I mean, I wanted us to walk through that, though. So, yeah. Anyway, whatever. That's a minimum spanning tree. You could output the edges that you want to keep, or you could spit out the whole graph. If it was like in our library, you could spit out the basic graph object or something like that. Okay, so let me turn those marks off. Now, one thing that you can do that's kind of cool with Kruskal's algorithm is you can use it to generate random mazes. I think this is a really cute application of this algorithm. You could think of this as a maze, right? We talked about this before, how to model different types of things as though they were graphs. And what you told me about mazes was, well, just pretend that like the maze has different walls and stuff, and there's different ways that you can go, and like I'll have vertexes be like spots I can go to, and the ones that have walls between them, I just won't put an edge between those two vertexes. We talked about that way of kind of thinking of a maze as a graph, right? So here's how to generate a random maze. You just make a graph like this, that's sort of a square or a rectangle, and you connect all the neighbors. So this is almost like a maze with no walls in it, right? Anybody can go any direction from any spot. To turn it into a random maze, just turn this into a minimum spanning tree, which will remove some of the edges, right? And when you're done removing edges, you'll have something with fewer connections. And then if you just draw like maze walls around all the parts that don't have edges, you got a random maze. So kind of cool. In fact, I think I can demo that. I didn't really try this before class, though, so I don't know if I'm a little scared to demo things that I haven't tried before class. This is the Trailblazer assignment that you guys are writing. In that assignment, you have to write the 4 graph path searching algorithms that we talked about. Oh, yeah, this is the Stanford map. Here, do you want to see how to get from grad school of business to Palm? Here's the way to go. This is no reflection on GSB students, keep in mind. I might prefer more of a Dijkstra type of solution. Maybe I'd go that way. That might be better. But anyway, you could do mazes. We talked about mazes here, like here's a maze, right? You could do randomly generated mazes in this program. I mean, you will be able to once you code that. And the way that you do that, where is it? Random maze, medium, go. And that, like all the other mazes, like if I say, maze 10 or terrain 6 or whatever, those come from files where it says put a wall here and put an open spot there. But the random maze one, I make up a maze that all the walls are open, there's no walls at all, and I give it to your code and I say, hey, run Kruskal's algorithm on this. And then when your code is done, it looks like that. And this is random. See? I can make a million of them. They're all just randomly generated mazes. Runs pretty fast too, huh? So let's see, I can just search for stuff, right? So I'm doing Dijkstra on the random maze that Kruskal's algorithm generated for me. So this all kind of goes together here. That's a cool example of using Kruskal's algorithm. That's how it'll be used in homework 7, taking walls out of a maze. Here's another. Oh, this is like an animated GIF of Kruskal running. But the problem is I can't control the rate of animation on it. So it just goes. And it doesn't even look very good on my computer. So you can look at it later. And it's just another example, which I stole from Wikipedia, the place I steal most of my best stuff from. OK, so here's the thing. When you're doing Kruskal, it's a little harder to implement than the pseudocode might have you believe. I think the pseudocode is fine. It does describe what you have to do. But I think when you really start coding it, some of these operations and statements don't line up real nice to easy commands in C++. I think one of the hardest statements to translate is this one. If these endpoints are not already connected to each other, add an edge between them. That sounds like a simple thing, but how do you know? Remember the picture a couple slides ago? Like, what is it? This? Well, I mean, I guess I meant like when we were halfway along doing this and we had like a clump of vertexes over here and we had a smaller clump over here and it's like, can this one reach that one or not? That's like a question that this pseudocode wants to be able to ask and get an answer to, right? Well, how do I know if one of these clumps can reach the other one? Well, I mean, you could think of things like doing a path search here and see if you can get to there. You could do stuff like that, but it turns out that really if you come up with the right data structures in this code, it makes it easier to answer this question. So what I would say is you might want to think, as you're implementing this algorithm, you want to think about what I would call vertex clusters, which are the clumps of vertexes that are able to reach each other through edges currently in this point in the algorithm. Initially, when the algorithm first starts, all the vertexes are all by themselves in their own individual clusters containing only that vertex. But as you add an edge to the algorithm, you say, hey, I added the edge between these two vertexes. Now they're in a cluster with each other, and everybody else is separate. And so this question of like, am I already able to reach you, is really rephrased as like, am I in the same cluster as you? If I am, then I won't add the edge. So like I put that edge in first. This is, I don't have the graph in front of me that produced this stuff, but I mean, just hypothetically, you know, I add those two guys into a cluster together. Then the next time through, the algorithm tells me to put this edge in. So now those three are all in a cluster, and everybody else is individual. Then the next time through, I add the edge to connect 4. Now they're all in a cluster, but these two aren't. And now the next time through, I add 2, and they're in a separate cluster. I mean, that's kind of how you do this. So really, you're thinking about, like, how do I store these clusters? How do I manage who's in a cluster? I'm going to move you out of that cluster and put you into this cluster. Sometimes, I don't think this picture illustrates it very well, but like sometimes one of the clusters has 4 people in it, and the other one has 3 people in it, and now you're going to connect them, and soon you got to merge all those guys together into one big cluster. And so sometimes it's not just about adding one person to your cluster, it's about adding several and this kind of stuff. So also you need to know things like, well, if you're looking at a given vertex, how do I know what cluster it's a member of? Let me find that somehow. So there's just, data structures can get a little tricky here. Like, what exact collections do I want to use? And I'm not going to tell you exactly what to use. It's the end of 106B. I'm just sort of hoping that you could look at a tricky problem like this and think about it for a while and figure it out. Maybe you and your partner talk it over if you're working on a team and try to come up with a good representation of this, you know? Now, so that's most of what I want to say about Kruskal's algorithm. Do you guys have any questions so far about how it works, or just generally what you do in Kruskal's algorithm? Kruskal's algorithm is not the only algorithm for finding minimum spanning trees. It's the only one that I will force you to implement in assignment 7. But there are plenty of other ones. Another common one is called Prim's algorithm. I'm not going to go through it in detail. I'll leave it to you if you want to look at it later. It's more vertex-based, whereas Kruskal's algorithm is strictly edge-based. They both end up in the same place at the end, and they're not all that different from each other. But I will leave it to you if you want to look at this. I've got an example of it on the slides and stuff like that.